In this video, we are starting section 8.3 on trigonometric integrals. So our goals are to compute integrals that involve powers of cosines and sines, integrals that involve powers of tangents and secants, and overall to recognize which antiderivative method we use. So in this video, we will focus on doing integrals that involve powers of sines and cosines. So let's get right into an example. Let's say I want to evaluate the integral of sine cubed of x dx. So it might be tempting when we look at this to be like, okay, can I do it in the same way as just the integral of x cubed dx? Because that would just be reverse power rule. I just add 1 to the power to get 4 and divide by 4. And of course, I have my plus c. But we've seen before that that doesn't work when you have something more complicated raised to a power. Just as a check, why not? Why does that not work here? If I were to do that and write sine to the 4th of x over 4, and let me ignore the plus c for right now, how could I check if this answer would work as the antiderivative? Well, I do the derivative of it and see, okay, will I end up with just sine cubed? Okay, so doing the derivative of this, the 1/4 in front is just a constant multiplying my function, so it stays there. And then we need chain rule for the derivative of sine to the 4th. The outer part is the power, so the power comes down first, and then I get sine cubed x, times the derivative of sine x, which is cosine x. But this extra cosine x that popped out from chain rule, it doesn't show up in my integral. And that's why this wouldn't work for my antiderivative. Okay, so we're going to need some other method. So I'm going to try this a couple ways. First, I'm going to call this attempt 1. Let's try a u sub. I see sine in the integral. Let's try letting u be sine. So u is sine x. Then du, its derivative would be cosine x dx. But this du isn't in the integral at all. There's no cosine in here. This is just not in the integral. So I'll put a sad face. Okay, that means that this is probably not going to work. In fact, even if I were to let u be cosine and have then the du would be negative sine, I'm going to run into the same sort of problem where this integral only has one of those trig functions. It doesn't have both, kind of like I would need to make a u sub like this work. So is there a way to get both of those trig functions in the integral? So it turns out, yeah. And this, I'm going to call it attempt 2. How do I get both sine and cosine in here? Well, I'm going to first split up the integral into sine squared x times sine x. And now for that sine squared term, we can use a trig identity. Because sine squared, remember, is the same thing as 1 minus cosine squared. So that's 1 minus cosine squared. I'm going to highlight that. And then that is multiplying that sine x dx. Okay, and now this is really nice for a u sub. So now this lends really well to letting u be equal to cosine x. Because then du is negative sine x dx. And I see that derivative in the integral just off by this constant multiple, this negative sign. I see that sine x dx right here. So that's an indicator that this is going to work really well. Okay, so if I isolate dx, I get du over negative sine x equals dx. So now let's sub in. So we are going to get the integral of 1 minus u squared times sine x times dx, and dx is du over negative sine x. Okay, we get a little bit of cancellation. The signs cancel, and that'll leave me with 1 here, and then down in the denominator, negative 1. So now to simplify, I can multiply this negative 1 times this term. That'll give me positive u squared minus 1 du. And now this antiderivative, we know how to do. This becomes just u to the 3rd over 3 and then minus u. Need my plus c. And then I got to sub back in. So u was cosine, I get cosine cubed x all over 3 minus cosine of x plus c. And we got it. We got our answer. So let's look at another example. For this next one, I have the integral of sine squared x times cosine to the fifth of x. With this one, I like the fact that we have both of these trig functions, sine and cosine. You know, I kind of need both of them in there to be able to make a u sub work. The thing about this that's not so nice, at least in the way that it's written, is to make the u sub work, whether it's this u sub or this u sub, I kind of want there either to be just cosine and not cosine to the fifth, because then this du would work perfectly for that cosine. Or I'd want it to just be just sine and not sine squared, because then this u sub would work out so perfectly. Okay, so we might ask ourselves, okay, could I use that trig identity like in that last example to split apart some of these terms? So what if we did it for the sine squared? If I did it for that, that becomes 1 minus cosine squared. And the sine squared would be gone. And now you just have cosines, no sines. But that's problematic. Like, I want both of the trig functions there still. So, okay, I probably don't want to sub in for that sine squared. Maybe I want to do it for this cosine. To be able to do that, let us split it apart as, so we got that sine squared in front. And the cosine of the fifth becomes cosine of the fourth times a cosine. So we are splitting away just one cosine by itself, because hopefully the du kind of becomes this. And now cosine of the fourth, that's cosine squared of x. That whole thing getting squared. So I'm going to be able to use my trig identity for that. So I got integral. So, okay, sorry. Let's do that trig identity first. This is going to become 1 minus sine squared of x. That whole thing getting squared. Okay, and now this lends well to a u sub. I really want this part to become the du. So I'm going to let u be sine of x. And then du would be cosine x dx. So if we do this u sub, we end up with the integral of u squared times 1 minus u squared, that whole quantity getting squared. And then that cosine x dx, well, that just becomes du. That just becomes du. Okay, now to evaluate this integral, we can expand out this quantity getting squared. If I were to FOIL that out, I get 1 minus 2u squared plus u to the fourth. Now I can distribute u squared to each one of those terms. And that gives me integral of u squared minus 2u to the fourth plus u to the sixth du. Okay, so now we are finally in a place where we can do this antiderivative. So we get u to the third over 3 minus 2u to the 5 over 5, and then plus u to the 7 over 7. And then my plus c. And then I got to sub back in. Doing that, I'll get sine cubed of x over 3 minus 2 sine to the fifth of x over 5 plus sine to the seventh of x over 7. And then plus c at the end. Plus c at the end. And we got it. We got it. Okay. So in the examples that we've done so far, we were, able to get it into a form where there was either just a sine separated like this with the dx or a cosine separated next to the dx after doing some algebra and doing some trig identities on one of the terms. Okay, it turns out that we can always do that when one of these powers is odd. When one of these powers is odd, I can split out just a sine, and then I have another even power term. Or this was a cosine of the fifth, that's odd. And I can split that out as a cosine times cosine of the fourth. But what if none of the powers are odd? So before I do an example where I just have sine squared, we're going to need some other trig identities to help us with this. And these are called the half-angle identities. So I'm going to need an identity for cosine squared and for sine squared. To get those, I first need to remember the following trig identity, which says cosine of 2x equals cosine squared minus sine squared of x. And now I'm going to do some algebra on this. I'm going to keep the cosine squared as it is. And then I get minus sine squared. I'm going to put a big old parentheses. I know is 1 minus cosine squared. So I'm getting rid of the sine terms. And if I distribute the negative, this becomes 2 cosine squared x minus 1. Okay, so I have cosine of 2x equals this. So if I were to rearrange the terms and isolate cosine squared x, I would get that it equals cosine of 2x plus 1, and then that whole thing divided by 2. And there we have a trig identity for what cosine squared x equals. And as we'll see, when we work out an example in just a minute, the key thing that's nice about this trig identity is it lets me take a cosine squared term and convert it into just a normal cosine without that exponent. And that makes it easier to do the antiderivative of. What about for sine squared of x? I can do the same type of thing, except now I'm going to plug in for cosine squared, because cosine squared is 1 minus sine squared. And then simplifying this, I get 1 minus 2 sine squared of x. So if I rearrange this, I'm going to move the minus 2 sine squared over to the left. And that'll be equal to 1. And then I'm moving the cosine 2x over to the right. So 1 minus cosine 2x. So sine squared, to get that, I just divide the 2 over. That'll give me 1 minus cosine of 2x all over 2. Okay, I'm going to highlight this as well. We have an identity for what sine squared of x equals. Okay, so why are these called half-angle identities? It's because the angle inside here is half of the angle inside of this. Okay, so let's see these in action. Let's do an example. So what if I want to do the integral of sine squared of x? So just like we saw at the beginning, I can't just do that reverse power rule. I can't just add 1 and be like, okay, I'm going to have sine to the third over 3. The derivative won't work out to this because I would have to do chain rule. Okay, so let's try using these half-angle identities. I know what sine squared x equals. So I'm going to get my integral. This 2 on the bottom is just a constant dividing my function. Let's pull that in front of the integral. And that'll give me a 1/2. That'll still leave me with 1 minus cosine of 2x dx. And now both of these functions are things that we know how to do the antiderivative of. We got that 1/2 in front. I'll put a big old bracket. Antiderivative 1 is x. And for cosine of 2x, so I have that minus sign in front, this will be sine of 2x. And then I need a 1/2 in front because when I do the derivative of sine of 2x, I do chain rule. And the derivative of sine is a cosine. But then the derivative of the inside is going to be 2. There's a 2 that pops out. And I need a 1/2 in front to cancel that out. Otherwise, a 2 would have popped out here, which I don't have in my function. Okay, so we got this. Let me close the bracket. And then I need my plus c because this is an indefinite integral. And we got it. We got our antiderivative. Okay, so just to recap, what are some of the strategies that we've seen in this video? When we have integrals that combine powers of sine and powers of cosine, if one or both of these powers is odd, then split up that odd power term so that I can separate either one sine of x by itself or separate one cosine x by itself. And we saw this in the first two examples. And the first two examples, in the first one, I was able to separate just like one sine x by itself. And the other one, I could separate just one cosine x by itself. And I can do that when I have an odd power term really nicely. If instead both powers are even, which happened in this example, then we have to use these half-angle identities. The half-angle identities. Okay, in the next video, we will see how we do trig integrals that involve powers of tangents and secants.